This is a demonstration of the Type 2 Optimization algorithm. Using index test data taken for all of the units in a powerhouse, reduced to power versus flow, where power here is given in megawatts and flow is in cubic feet per second. We can generate a set of curves. This is power versus flow. These are the efficiency versus power curves for each of the units in a powerhouse. Notice how different they all are. And this characteristic is what makes the problem of load sharing and unit selection in a powerhouse so difficult. First part of the algorithm is to import the data files from their Excel format into this program. And this can take anywhere from 7 to 26 seconds because each of these Excel files is being opened in the background, the data is being imported, the file is being closed, and the next one's being opened. Once it's open, we can uncheck this box, run our algorithm again. You notice the calculation time has decreased pretty drastically. So that's under a second for 14 turbines in a powerhouse. You'll notice this column here, the rate of change of flow versus power. This is the derivative of our power versus flow curve for each of our units. And the ideal solution will have each of these derivative curves match. As we approach the maximum available power in the powerhouse at a given head and run the algorithm, these dq/dp curves are blown apart because the turbines are all operating outside of their optimal efficiency zones. Now as we decrease the power output setting in the powerhouse, the algorithm will start to choose units to drop offline based on their peak efficiencies. This allows the overall efficiency to stay above a certain level and provide optimal efficiency even as the power decreases. As we decrease the megawatt demand, more and more units get dropped offline. Now another important part of this algorithm is the ability for the operator to choose which units to use in the calculation, because sometimes units are out for maintenance or they shouldn't be included in the algorithm for one reason or another. In this case, in this development version, we just set it up to choose manually which turbines won't be included in the algorithm. So we run the solution again, and you'll notice that all of the operational turbines are the ones that are still active, and their slopes match, which means we have an ideal solution. These units are still being considered in the solution, these that are at 0, but are still active, but their peak efficiencies are too low to justify including them in the solution. Now we can also solve for various levels of head. This is something that could be incorporated into the metering directly in the program so that it updates automatically, or the operator can do it. You can just key it in before running the solution. You notice that the efficiency is changed and the maximum power output available changes as you change the level of head. Put this back to the original setting so that I can get my bearings. Now our max power available from the powerhouse is 1372 megawatts, and if I choose something out of bounds, the algorithm will just zero out the table, indicating that it can't find a solution because we've chosen something out of bounds. In addition to being able to manually select active or inactive units, we can also define nonlinear constraints based on the individual needs of any particular powerhouse. These are things that can be incorporated into the algorithm on a case-by-case basis. And with that, I will conclude the demonstration, and I hope you won't hesitate to get in touch with me if you have any questions.